welcome. My name is Simon, and today I'd like to talk to you about sketch algorithms. How many of you have already heard about sketch algorithms before? 2 hands, 3 hands, okay. So, well, the rest of you are going to learn some awesome new ways of working with data. So kind of the general idea behind sketch algorithms, and that's kind of a huge and ever-growing family of approaches, is that instead of working on our data directly, we want to summarize this data in some data structure and then query that rather than kind of doing direct operations such as calculating an average or something. And like, the reason why you might want to do this is especially when you're handling large amounts of data. Like anytime you're in a streaming setting, it's very becomes very convenient that you can do this kind of calculations on the fly. Or also when you aren't really kind of sure with how large of a data you're working, or you're working on very constrained devices. For instance, a lot of my experience with sketch algorithms came from my work on Metabase, which is an open source analytics and BI tool. And like one of the things we're trying to do is build a data scientist in a box, so doing like various analysis for you of your data. But the problem we have is that us being open source, there's a huge variety of people who run us, and it's all obviously done on premise rather than the cloud. So on the one hand, you have people on like those super tiny VPSs running a database with maybe a couple hundred rows, and on the other hand, you have huge companies running us on data warehouses with hundreds of billions of rows. And for both of those users, like our product kind of has to work, and we can't really kind of bring the server down something, although something which sadly happened in the past. And to make it even worse, like some of those databases are going to be optimized for analytics tasks and some aren't. So there's always this kind of a balancing act between what kind of things we can just offload and compute in the data warehouse and what kind of stuff do we have to compute on our own. And ever since we started using sketch algorithms, predominantly Histogram, which is the first one we're going to look at today, our capabilities in terms of what we could do with data grow immensely, because a lot of the constraints we previously had about performance and memory usage and so forth flew out of the window. So, as promised, the first one we'll look at are histograms. It's the first, and also I think it's by far the most useful in the biggest variety of cases. So it's like definitely one that makes sense to have in your tool belt. And the general idea is super simple. Like basically, what we want to do is we want to capture our empirical distribution, like our actual data, in a k number of buckets, and then use those buckets, so that this histogram representation, to compute various summary statistics from that. So summary statistics here being things like the average, variance, and stuff like that. Like basically, and especially like useful things like quartiles and things like, so the usual stuff you'd want to do with data in an analytics setting. So the idea is kind of simple, and luckily also the algorithm itself is pretty straightforward. So if we look at this simplified or very basic implementation of how it looked like of constructing a histogram, we pick a number of buckets, let's call it k, and like this number kind of depends on your needs and memory available and so forth. But in general, like anything above 64, you already have a pretty decent resolution, and it very rarely makes sense to go above, I don't know, 250 or thereabouts. But pick the number based on your specifics, or just use the default, and it's usually going to be fine. So we have our buckets. At the beginning, like they're all empty, just showing a count of 0. Then we have values coming in, and for each value coming in, we first look if there's already kind of a bucket centered on that value. And if it is, awesome, we'll just increment the count for that bucket and we're done. If it's not, we're going to add another bucket centered on that number and set this count to 1. So we're kind of counting things. And this kind of, if you have lower cardinality, if you have less distinct numbers than the number of your total buckets, you basically have the perfect, you perfectly captured the distribution and you're kind of done. But where it becomes kind of slightly more interesting is if you have more different numbers than you have buckets. Let's say you have real numbers, so kind of huge variety of them. Then what happens is, once we go past our k number of buckets and still new values are coming in, what we do is that we add another bucket. So now we're in a situation where we have k plus 1 buckets, which is something that we don't want to do. And then we look for the two buckets that are the most adjacent, like they're closest together, and merge those two weighted by their counts. So like it's not going to be like halfway between them if the counts are different, but it's going to be tilted more towards one and the other one if one has more values than the other one. And then kind of rise and repeat that. And if you kind of think about this construction, a nice property of it is that we essentially get the merge operation on histograms for free. Meaning that just as like we already have to merge buckets when we passed the k number of buckets, like the same thing can also take two fully built or partially built histograms and merge them together using the same rule of finding all the adjacent buckets and then just kind of recursively merging them until you end up with just one histogram of the entire size. And that also means that it's kind of, even though like histograms capture distribution, it's never, like it can always be live. You can always stop it up as new data comes in, which is a fantastic property if you are working in any kind of a streaming setting, because you can just kind of continue filling it as the data comes in. And also, this super nice merge property means that it's rather trivial to do it in parallel and just kind of merge results. So you can do the kind of the perfect school-like example of MapReduce and do this on a massive scale if you need it for some reason. Right. So now we've built our histogram. So how to use it? The idea is that like, we're going to estimate values. So like the thing is, and this is kind of the idea behind all the sketch algorithms, that what we're willing to do is we're willing to trade some of the precision for a much faster and more benign algorithm in terms of how expensive it is. So the values we're going to get out are not going to be precise. They're going to be approximations, but it turns out that for a large case of analytics tasks, they more than suffice. So as we previously said, if we're kind of lucky and we have low cardinality data, meaning like our cardinality is less than k, then for the most operations, we can get pretty exact results. But if not, we kind of have to do some math, but it's still kind of very simple. So basically, the assumption behind all this is that our distributions are kind of relatively well behaved and that you can assume that the mean of the bucket is also its median, meaning that like it's basically half of the values fall to the left of the mean and half of the values fall to the right of the mean. If kind of that's not the case, your accuracy is going to suffer somewhat, but in practice it turns out that like they tend to be pretty robust. So this is not something you have to be super mindful of. Anyhow, so with this kind of assumption, what we're essentially going to be doing is we're going to be doing weighted interpolations for all our operations. So if you want to do something like sum up, like do a cumulative sum up to some value, what we're going to do is we kind of found the two buckets on each side of our value. So we know that our actual, and kind of, then we can do the left side, essentially like do it precisely to its lower bound, and then for the rest, we just do kind of interpolation between the lower bound and the upper bound, and kind of estimate what the value should be between those two. And it's kind of the same idea behind all the operations you would kind of do with histograms. So find the nearest buckets and then do some math, which is usually just some form of interpolation or weighted interpolation, and figure out what the value kind of should be. I'm going to look at an example how to do it. This is closure, but like I hope it's not going to get too much in the way, and the principle is like super simple. So in the first line, we just build a histogram using like a reduce functional operator, essentially just kind of going through 10,000 random numbers and inserting them into our histogram. And as pointed out previously, this is not like in this case, I'm just doing it for all the numbers in one go, but I could kind of build this incrementally and add values as they came available, or if I would kind of stream results from my database or have some kind of a lazy collection, can do it slowly. And then you can see that, so we've built our data structure and store it into a variable called age. Horrible naming, I know. And then what we do is like we just kind of get a couple of statistics out from it. So we look at its variance, some number, and then like percentiles, for instance, are already kind of something that's much more useful, and it's also like something that you can't readily get from if you just want to do like normal statistics. Like something like variance, there are well-defined classical algorithms to do it, even like single pass and everything. But something like percentiles is a tad more tricky. So here, actually, kind of, it makes sense to use a histogram just to get those estimations, even if otherwise like you don't need all the nice properties of histograms. And last but not least, we also have this kind of a notion of as a representation of this is essentially how our histogram is described. So we have the means of different buckets and then the counts for each of them. And so kind of have this more plastic idea of what's going on here. So if we would add a new one with, let's say, a mean of 0.05 or 0.558, then we'd kind of slot in here, and then we'd search for the two most adjacent ones, which would be these two, and we would merge them and have a new value to keep the number at k. Right, so like with this kind of in mind, and kind of the rest of the talk is going to be like how to use this and how to kind of, why is this an actually kind of a cool tool, or why is this something that I think you should look at? Because like, to be honest, I don't think our conference talk is a very good medium to teach you about the ins and outs of how to implement histograms and stuff like that. But like what I would like to do with this talk is kind of to inspire you to research this and to see if this can kind of potentially be a fit to a problem you might have or you will face at some point in the future. So kind of the second nice property is that it essentially decouples data collection from computation. And this kind of decoupling is always turns out to be a very powerful thing to do. Even there said that, for instance, like a lot of the virtue of Clojure, the programming language, is exactly that it acknowledges that how important it is to decouple things and how you then have much more powerful building blocks. And here we have something similar with regards to doing analytics. And kind of in practice, what decoupling here means or gives you is predominantly a way to persist kind of your computations. So you don't, otherwise, especially if you're in a streaming setting, you have this problem that it is going to be gone. So what you can calculate, awesome, but then the data is gone, and oftentimes you'll have very hard time recovering it, or maybe like can't even recover it at the resolution that you had. So you're going to have to decide upfront all the operations you want to do. And if kind of something new comes along, you have to kind of change all the code and all those things. And it's also like, with that, composability always suffers because you then have to make decisions basically on the level of the entire processing pipeline where what gets calculated, because you might not kind of then have raw data available downstream anymore, something like that. While with something like histograms or sketch algorithms in general, because what we do is that we encode our data as a data structure. It also means that we can easily persist it, serialize it. Like, if you remember, like back when look at this. This is basically just a hash map with two different fields, and that's it, or a list of hash maps. And it's easily to see how you can just store this in a database or something and restore it at a later point and work with it. And that gives you a lot of flexibility in terms of how you can approach processing your data and how much do you have to kind of think in advance, and also how much you have to complicate your architecture in advance. The next thing is that it's just when doing, now kind of moving from the operation side to the exploratory analytics side, it's very, very convenient to have distributions readily available. And it's like one of those subtle things that you don't really kind of realize what you're missing until you start working with tools that give you this affordance to, at every point, kind of see what kind of distribution you're working with, visualized, and so forth. Just kind of an illustrative example of why you would kind of want this. Just kind of look at those four charts, like kind of like pretty different. Yet, if you kind of start going into summary statistics and calculate things like mean, variance, correlation, and so forth, it turns out that they're kind of all the same. Like you can't tell, based on all those statistics, you can't tell them apart, even though they are very much kind of look different. And it turns out that you can, like, if with some trial and error, you can even fit a dinosaur to have essentially any kind of a distribution, any kind of summary statistics you want. And this is a problem, because if you just live in a world where you describe your data by those numbers, you oftentimes miss that like very different things are happening. For instance, if you compare here let's say the two top one, the one on the left and the right, it's probably like it seems that there is something kind of happened with x2 around like data point 10 or something, and we have a reversal in trend. And this is something that kind of we would completely miss if you just look at the various summary statistics. While if it's you kind of visualize it and look at this distribution, a lot of those things will become apparent. So yes, when working with data, do try to kind of think with distributions. This also gives you kind of a nice additional bonus in terms of that you can have much richer similarity metrics. Like a thing that you'll, when working with data, that you'll often want to answer is like in some form or another the question: are these two pieces of data kind of similar or not? And like the trick is that with a lot of real-world data, like we are going to have some noise. So it's not going to be a question of are they the same, but are they kind of roughly the same? So basically, we want to do kind of some sort of statistics test to figure out how similar they are. Now we know the kind of the basic statistics approaches of doing a t-test or something like that, but a lot of those things have pretty strong limitations on what kind of distributions they work well with, and otherwise you're immediately kind of playing with either type 1 or type 2 errors, or you're too selective with what you deem to be similar, or you think that things that are absolutely not similar are similar. So it's kind of a messy thing. But if instead of you look at your data as fundamentally a distribution, then you have a whole new family of similarity metrics defined over distributions that you can use. And those are often way more powerful and way more robust than other measures. So just by being smart with how we represent our data, we suddenly gain kind of this wealth of mathematical approaches of how we can also work with our data. And suddenly, like the thing is, with often like many things I'm talking about, like might going to seem like just small improvements. But one thing I'd urge you is to think about the affordances of tools you're using, because oftentimes, like if you have the right tools available, you can just kind of recast a problem to something that you can solve very well. And this is like where the power of kind of more advanced approaches often shines. It's not just like those gaining, I don't know, 5% in speed or precision or whatever, but just like radically thinking your problem in a different light, and it's in a light that kind of gives you much more power or much more leverage with the tools that you have available. Another kind of approach that I very much like is kind of this notion of having different time slices. Basically, imagine you're in some streaming settings, so kind of data is coming in, and you're kind of building histograms of it. And then like one thing that's kind of nice to do is to just periodically essentially snapshot your data, let's say on a daily or hourly level or something like that, and kind of have that. So like you don't, the first like, when you do that, if you're fine with this kind of being your ultimate resolution, let's say a day or something, you don't even kind of have to keep all the data, and sometimes that's not even kind of feasible to keep all the data. And still, like by virtue of how nicely histograms can be merged together, you aren't then stuck with having your data that resolution, but you can easily also kind of just upscale it to any other higher resolution, and everything just kind of works. Because otherwise, it very quickly gets tedious if you have aggregated data in one resolution, so let's say per day, and then you want to kind of upscale it to per month or something, and then you have all that mess of how do I combine averages and how do I combine mean and maximum and stuff like that. So like it's kind of it gets pretty hairy mathematically quickly, and oftentimes it just turns out that you maybe don't have all the correct data to actually kind of reconstruct your distribution at a higher granularity. But here with just essentially, if you work on the level of histogram rather on the level of math, you can just kind of merge them together and have a representation instead of, let's say, per day of per month or something like that, and work with that. And this gives you, again, like a lot of flexibility in terms of how you save with it, and kind of allows you to defer a lot of the decisions that otherwise carry a pretty heavy burden in terms of architecture and DevOps, and you can kind of defer them and just have a flexible base representation and then build from that whatever you need. Also, once you have something like those time slices, you can then start comparing them. And like one thing that I've also kind of realized working longer and longer as a data scientist is that a lot of the problems are kind of also time series problems, but we just kind of don't treat them as such because they're like on the first order, there's something else. And then kind of oftentimes working with time series data is kind of messy, or like at least not very convenient. So we just ignore this time component focus on the kind of simpler first order problem. But if you have something like those kind of time slices, you can kind of recover a lot of this time-wise information as well, and you can start looking at kind of, you know, trends of how various my statistics are changing. Something like, what's the trend of how my variance is changing through time? This is something like if you're doing some sort of, let's say you're doing an analysis of some A/B testing or something like that. Like that's a kind of very important question that maybe what happened during the test was that your customers have become more and more diverse, so you kind of have bigger and bigger variance in some of the variables you're looking at. And this is something that's going to kind of impact your test, or maybe it's even cause enough that you should rerun the test because it turns out that there is some external factor that changed what kind of data you're working with. And a lot of those things, if you just look at the overall population, get hidden that, you know, it might from 10,000 feet up, when you're just looking at the entirety of your data set, it might seem like reasonably representative, reasonably homogeneous, so you're okay, it's fine. But if you look at it on a day-per-day level, you might see like huge shifts in your distributions or some behavior that you otherwise miss, and it can have big impacts on how you then actually deal with this data, and also just what kind of conclusions are you willing to draw from it. And having like this time slices is exactly like a means to do those things. Like again, all those things you can do them normally as well. Like if you suspect that something like variance is going to be changing, yes, you can do kind of running variance or something and then plot that and you'll see it. But again, it's kind of here, the nice thing is like just again, affordances. If it doesn't cost you almost anything to view these, it's something that you're going to be using more often as you do your analysis. And also similarly, it's not something you have to already kind of figure out when you're figuring out how you're going to acquire your data, but rather if you kind of see something weird, you can go deeper. You can explore your data more by looking at those things, even if you haven't kind of made a note of tracking this at the beginning, just because you have that much more of a flexible and powerful representation of your data. Kind of another useful trick is what I call kind of the sampling trick. So kind of the idea is that we're again working with massive amounts of data, and unfortunately, like not every algorithm can be turned into being kind of an online. I mean, like you can't do everything just in a single pass through your data. But at the same time, it's often like going to be very, very awkward if you want to kind of keep your data in memory or do it a couple of times or something, or might even impossible. So one thing that you can do instead is that you can summarize your data with a histogram and then sample from the histogram. It's kind of another nice thing that kind of histogram can essentially just produce an infinite number of samples from the same distribution. So those aren't going to be exactly the samples of values that you had, but anything like that falls on that distribution. So kind of essentially, you can call it that it's kind of in a way bootstrapping, but with perturbations, meaning like data is always going to be like slightly changed, and so it's also kind of can be sometimes useful when you just need a lot of data in terms for, let's say, training some machine learning algorithm or something like that, and just kind of generate a lot of it from basically just figuring out what your empirical distribution is, encode that in a histogram, and then you can get as large as a training data set you need from that histogram. Now, up until now, we kind of just talked about, obviously, numerical data and pretty simple at that, but it also like there is one refinement that you can do to your histograms, which kind of is usually called targets, or the terminology is like not supersets, so sometimes people also use different names. But the idea is that instead of just kind of treating things as numbers, you can also attach additional dimensions to your data. So you can kind of like, let's say, a segment of your users or something like that, and then essentially have distributions for each of those targets. So you do get at least some notion of having at least slightly like conditional probabilities or something like that with tracking the targets as well. And kind of the idea is that now each bucket that we have is also like in itself. It doesn't hold just its mean and count like we had before, but the idea is that each bucket then becomes like a mini histogram of it in of itself, tracking all the different categories that fell into that. Of course, like this approach does have limitations in terms of if you have huge amount, like very high cardinality of what you would use as targets, then you'll encounter problems in terms of just memory consumption. But again, for a lot of cases, it turns out that you're just basically interested in maybe a couple of dozen categories at most, or even less than that, and then you can still have a pretty kind of efficient representation and retain that conditional this probability aspect of your data that would otherwise be lost. But still, what about if we want to kind of go even like one step further in terms of categorical data? We just have categorical data and we have heaps and heaps of it. Let's say you have something like you're indexing the internet or something, and you're looking at the number of incoming links, and you want to know like what are the top most linked to pages are, and like, even maybe something and something similar. Here, like any kind of normal counting approach won't work, because simply like if the cardinality is large enough, you can't, like, you don't really want to hold all that in memory. So we want something kind of more efficient, and this is where algorithms such as count, min, sketch come in. And so this is here we're moving away from histogram to our example, which I think that's kind of nicely illustrative of a lot of the ideas behind sketch algorithms. So I want to kind of dwell for a moment on that as well. And kind of the idea of count, min, sketch is that we're kind of going to estimate what the minimal cardinality of something kind of is, or we're like some bound on it. So the idea is kind of that we construct a grid with let's call it W amount of columns and D amount of rows. And like here, the two parameters W and D are going to kind of determine our both our time and space needs, as well as the error bounds on our estimations. So kind of play with those and then get different error estimates from it. And then what we're going to do is that each row is going to be associated with a hash function. And here the subtlety is that you want to pick those hash functions to be pairwise independent and bound to interval from 0 to whatever W stands for here is. Now the pairwise independent kind of can be messy, but there are heaps and heaps of libraries that do that for you. So just pick some crypto library which already does that for you, and Bob's your uncle. Okay, so we now have our grid. We have our the number of hash functions, and then as each new observation, as each new piece of data comes in, what we're going to do is like we're going to go through all the rows, and for each row we're going to apply the hash function to our data, and that's going to give us some number between 0 and W. And we can call this number K. And that's going to be our column index. So in each row, we're then going to increment the value with that column index. And then like the last step, and now we so essentially, and this is kind of the I guess, counterintuitive part. For each new data point, we're actually going to make D numbers, so as many of rows we have number of increments of some of the values in our grid. And then to estimate the frequency of some event, we kind of do sort of the reverse. So we again calculate its index, so we see where it falls, and then we just kind of look through all the rows and find the one with the least value. So kind of a graphical representation of the same thing. So get value coming in, then we calculate all the hashes, and then those give us the indexes where we want to increment the count, and then to find the estimate of at least how large of a count it is for the value. We just find the row with the least value. From here, the name count min comes. And now, what you might now be thinking is, but surely this is going to be like grossly overstating the count. And the answer is kind of yes and no. So yes, in the sense that, absolutely speaking, yes, the values are going to be too high. But it turns out, and this is, I guess, one of the beauties of sketch algorithms. It turns out that oftentimes, you don't really even care about the absolute number. That you're quite content if you just can pluck out, for instance, the 10 largest values or something like that. And for operations of that type, something like count, mean, sketch is perfectly adequate because you don't really care about absolute values just as long as you can have this rough ranking, which turns out to work reasonably well, even though maybe position 5 and 6 are going to be changed or something compared to the actual values. But again, oftentimes that is kind of good enough. And so I think like one of the, especially like if you're coming from the more engineering side to data science, like a problem, at least a problem that I kind of had, is that oftentimes you think too much in absolutes and you want this kind of perfect result, while it turns out that the real world is very messy and you're going to have like various sources of errors anyways, like various uncertainties anyways. And so oftentimes it's also kind of fine if our algorithms introduce some of it, because it's still kind of, the end result is going to be good enough. It's going to be good enough for the business needs or whatever. So like the trade-off between the time it takes to produce an answer versus the quality of the answer is going to make it worthwhile. Like one thing that kind of occurred to me as I was working more and more as a data scientist is that speed of answer matters dramatically. And there's like a huge difference in how an organization can utilize data science based on how fast you can provide answers. And like it feels there are like kind of essentially 3 different categories in terms of how fast you can answer a question. Like the first one is, and like the numbers here are obviously going to be made up, but just for illustrative purposes. Like the first one is probably like 2 minutes or less, and that means that as like you're in a meeting, as there's a brainstorming going on or something like that, you can just pull out the answers and answer here and there. And this is obviously kind of the ideal. Like if setting up an analytics or data science department, this is like the speed to which you want to aim for. And that means like 2 things. First of all, you do have to have tools which are expressive and powerful enough that you can actually pull out the answers relatively quickly instead of spending a lot of time coding around them or something. And also it means that you want that the whole thing has to run fast enough that you actually get answers, because otherwise it might be quick to just type a couple of commands, but if it takes then 15 minutes or an hour for you to get results, again, you have this huge delay. So this is another reason why sometimes it makes sense to reach for something like sketch algorithms, just because they provide answers faster. And that's oftentimes like way more important than having that last percentage of precision. So that's our first kind of class. The second class of how fast you can answer is, let's say, 20 minutes or something like that. So like the idea is that it's something that you can probably stuff somewhere in your day without having to kind of properly schedule it and everything. And that's still kind of, oftentimes that's reasonably fast enough. But like the moment it's more than that, it means it's probably going to end up as part of some next sprint or something like that. And that immediately means that it's going to take 2 weeks, maybe even more, for you to give an answer. And oftentimes that just means that people are not going to use data. Like maybe you'll get to give the answer, but oftentimes the decision is going to be made way before that. So, and that's going to drastically reduce the value and of your department, what you're working for. So do kind of consider how you can stack the deck in your favor in a way that you can kind of provide fast answers and kind of have the entire kind of organization also focused towards that, and acknowledge the differences in affordances of tools and how those shape the way you solve problems. So kind of to wrap all this up, kind of I think, key takeouts that I want you to take away from this are that persistent computations are a very powerful building block, not just when talking about analytics, but almost like in any context. If you can essentially encode your computation into data, it just becomes much more powerful, much more flexible, because it gives you all those new options of how you can introspect your data, how you can work with it. You can save it, you can restore from some previous state. You don't kind of have this, if something goes wrong, you can just continue from some checkpoint in the past rather than having to redo everything where data might not even be available and so forth. So do kind of always look into how you can encode your data, encode your computation into data structures. This is also just like incidentally, like I think like one of the strong points of functional programming, and especially like languages like Clojure, is exactly this focus on encoding as much computation as you can in data structures, kind of being very data-driven, as it were, programming where data comes first. And that really gives you a tremendous amount of flexibility in how to kind of solve your problems, and especially when you're kind of not really sure how to solve them, when you're in this exploratory mode, just like playing around, having something that you can kind of poke and experiment with is a huge, huge boon. So, second thing, distributions are awesome, and it's very good that like, you force your thinking when you're working with kind of numbers or in statistical context, that you try to think more in terms of distributions rather than in concrete numbers or some kind of summary statistic like that, because they give you like a much richer insight into what your data is and how you can reason with it. Because like, oftentimes, I mean, the reason, if you think about it, why we do summary statistics is to give us a human thinkable handle on our data. So we want to kind of simplify our data in a way that it's easier to, kind of to reason with. But that often also kind of carries a cost that you make some hidden assumptions, and maybe you aren't even kind of aware of those assumptions. But like, there's a huge difference in terms of how to think about your data if you have like a simple normal distribution, or if you have like two humps or something like that. Like, there's like a lot of information that's kind of otherwise usually hidden, or you just kind of find it in very obscure statistical measures which don't have this kind of a nice and human-friendly explanation. While if you look at the distribution just graphically and think about it as a distribution, this becomes apparent and even kind of a first-class citizen, and gives you a much richer understanding of kind of the type of data you're working with. And also kind of relatedly, do also think about that a lot of the processes that we're analyzing, even if we don't really kind of acknowledge it, are kind of situated in time. They have this at least latent time component, and oftentimes when, especially when working with kind of real-world data, like that data is going to be kind of changing as our experiment is running, as our product is running, or whatever. And like, also try to capture those things. So do have some way of tracking how even your distribution is changing with time, how your various metrics that you're following are changing with time, rather than just kind of looking at the current snapshot or the snapshot over all the time, or something like that. Third of all, approximations are oftentimes kind of good enough, especially because the trade-offs that they entail in terms of it might be just so much more simple to calculate them, or just like so much faster that it makes sense to give up some precision. And oftentimes, when you think about it, you aren't even giving up anything, because the ultimate answer or result that you're interested in doesn't even need that precision, just needs maybe some sort of ranking or finding something, or maybe you can just kind of first use something like a sketch algorithm to have a rough idea of what are our potential candidates, and then using some other algorithm to kind of fine-tune the results and get the actual kind of numbers if you need more precision. And kind of last but not least, you can get surprisingly far with working with very large amounts of data, even on a single machine, even on like a simple laptop like this, if you're kind of smart about how you work with your data and how you encode it. And I think that, again, flows into this kind of, we want to have as little friction as possible when using it. And it's still kind of, no matter how nice of a distributed computing system you have, it's still much more convenient if you can just kind of run things on your little laptop and still have results in a decent amount of time. And just kind of the complexity, both in terms of what you need to think about, and also just like all the infrastructure work behind it to have distributed computing, oftentimes just kind of doesn't make sense, or it's like it's already expensive, and then what happens otherwise is that we make this kind of compromise of just not doing some things with data that we could have, because it just feels too much work to get the results that we need. But if you're kind of smart about it and do things such as use sketch algorithms, you can kind of leverage your data way more and become way more efficient with how you work with it. And on kind of this note, I yield the floor to you and any questions you might have. Thank you.
Hi. The histograms you showed were based on univariate data. So for each bucket, there was the average value and the number of occurrences.
Yeah.
There was nothing about time. So could you clarify how it helped us in recognizing those peaks that are visible only for small time frames?
Right. Imagine that you build a histogram like that for each hour or some whatever unit or day or whatever makes sense. And then what you do is you would essentially for each of those like daily histograms, you might calculate something like variance, and then with that you have like a series of variance per day, and you compare that. So it's it's not like here the idea is not to directly encode this time information in a histogram, but rather in the metadata in terms of how you save those histograms or refer to them and say, okay, this is the histogram from day 15 and that histogram from day 16 and so forth, and then assemble them together. Of course, here the trick is, or like it's not a perfect solution because you still have to figure out what your ground resolution is going to be. But very often, like you can have a good idea of what that should be. Like for instance, if you're working with business-like data, probably a day is going to be sufficient or something, or like. Usually, like you have a pretty good idea of what's the minimal resolution that you're reasonably going to need, and it's more like a question of then how that resolution and higher things are going to be changing.
Thanks. I've got one more question.
Oh, of course.
In the algorithm of merging buckets,
yep.
You need to find the two closest buckets.
Yes.
And you mentioned that it works well for MapReduce, that it can be done in parallel. But it's not clear for me. If you need to find two closest, then how can you handle that in parallel? There is always only one pair.
No, in parallel in the sense that essentially what your MapReduce would be, like you would partition your data in some way, and then for each of those you would build its own histogram, and then you slowly merge them together. So the idea is that the map phase is going to be build a bunch of, I don't know, let's say 1,000 or something histograms, and then during the reduce phase, you're going to be slowly reduce those histograms just to one, so merge two and two and two and two together and build one. And due to the properties of how histograms are built, you can do that and not lose any information. So it is essentially from the perspective of constructing a histogram, it's the same whether you add a new element to it or you add an entire new histogram to it to build it up. So that's why it doesn't really matter what number of histograms do we start with, and then as long as we can just fold them together into one.
Can these approaches also work effectively if the histogram values that you're bucketing aren't single-dimensional scalar values, but say two-dimensional values in some area, or like spatial coordinates, for example?
Like for spatial, you do have some specific data structure that does similar, like if you're actually working with geodata with roughly the same idea. But in general, this is where the notion of when we're talking about targets comes in. So, I mean, it is targets aren't a perfect solution, and if you do have a lot of dimensions that you want to capture to get this distribution, this is not going to be a good enough approach. Then if you want to summarize that, you'll probably want to have something machine learning-y and build some form of multivariate kernel or something like that to summarize your data. So there is a limitation there, but if it's just a couple of dimensions, especially if those dimensions are discrete rather than continuous, then you can make it work with histograms. Well, if anyone has any questions later, just track me down. I'll have to talk about this stuff. Just feel free to come and say hi. And thank you.